in, yeah?
Yeah.
Okay.
Yep.
You have a week until, or you have around 10 days until. It's better to get everything sorted out before your first written paper, essentially. Okay.
Okay.
How about registration for the thinking skill assessment? Have you sorted it out yet?
I already filled in the form, but I haven't handed it in.
Okay. Again, I think the deadline is 30th September, but there's an international deadline, so it needs to go back to GIS way before that, I think. Okay.
Yeah.
So make sure you don't miss that. Anyway, going back onto that equation I show you and I asked you to draw. Can you like separate the two equations and draw them separately and then show me the graph?
Yeah, I already did. This is the first part, and then this one is the second one.
Okay, r is greater than 0, so you can cancel the other bit. So when you take the two equations together, how do you think the graph will look like?
The A over R 12 one would decrease faster than the B over.
Why is that?
Because the denominator is squared, so if it increases faster, that means.
What do you mean the denominator is squared?
6 r to the power of 6, the whole thing squared is r to the power of 12.
Okay. So do you mind drawing me like how it would look like in your opinion? So you know how each of them will look like individually, and then think about the collective equation and see how they will look like.
So A over r to the power of 12 should decrease faster.
Okay.
B divided by r to the power of 6 should decrease, but then not as fast as the first one. But then there's a negative, so that means it is reflected against the the x-axis.
Okay.
So something like this.
Yeah, but when the two terms are together, like the first minus the second one, how would the graph look like? You think it would look like the dotted line you said?
Well.
But it wouldn't be that because so A and B are just constant, and then okay, let's talk about it in terms of the physics there actually. So this is an equation describing the potential energy between two atoms. So you know, like atoms, what holds atom together? So you have two atoms. So let's say these are not forming a covalent bond, at least not yet, but there's interaction between the two atoms. So what do you think exists between the two atoms? What kind of forces?
The electrostatic forces of attractions.
Yeah. What about it? Tell me more about it.
According to Coulomb's law, if there's two charges.
What do you mean by two charges? How come there are two charges? We're talking about atoms.
Atoms have nucleuses and electrons.
Mm-hmm.
So the nucleus is positively charged.
Mm-hmm.
The electrons are negatively charged.
Okay.
So there would be force of attraction between the nucleus and electrons.
Okay.
The nucleus of the atoms, electrons of the atom. And then there's also repulsion.
Oh, what about repulsion?
The electrons of one of the atoms with the electrons of the other atom.
Why would they repel?
Because both of them are negatively charged. So like charges repels with each other.
Do you think the nucleus repel with the other nucleus as well?
Yeah.
Do you think the nucleus and the nucleus can ever get to each other?
No, that will be the potential energy is too
Why
high.
not? Suggest why not? Okay, but also you think about it before you reach the two nucleus and nucleus together, the electrons have to come together first, and because the electrons are in the kind of like they're rotating around in that fixed area, right? Like spherical area, spherical volume actually three-dimensional around the nucleus actually. So before that even happened, the electrons already repel each other. So you talk about this attractive force and a repulsive force, right? So in terms of this potential energy, so this is a model for this interaction energy, the potential energy between the two atoms, where there is an attractive force and a repulsive force. Which term do you think contributes to the attractive, and which term do you think contributes to the repulsive, and why?
V is the potential.
So V is a function of R because depending on the radius of, if you have two atoms, so if you fix one of the atom, then the distance from this atom which move from that, it's like a particle on a spring. It's like at a distance r away, right? Okay, so there's the distance r. So as r changes, potential energy changes, and then the amount of attraction and repulsion will change. My question is, okay, so V is potential energy, is a function of R. It changes when R changes. So which term do you think is responsible for attractive forces, and which term do you think is responsible for repulsive forces?
If the A over R 12th term is very high, then VR would be positive, which is repulsion. So the negative V over R to the power 6 one because it's negative.
Sorry, which the R to the power of 12 or R to the power of 6 is repulsive?
R to the power of 6. Oh, wait, repulsive. R to the power of 12 is repulsive.
Okay. Can you explain again why you think that is?
Because potential energy is to move the test unit charge from infinity to a point. So if it's very positive, that means to move it from infinity to that point will be very difficult, which means repulsion.
Okay, cool. So yeah, right. In a way, the negative potential is good. So the graph of 1 over r to the 12. Do you have that graph just now?
Yeah, it's this one.
And that's the repulsive, right?
Yeah.
Yep. And then the minus 1 over r6 is the attraction, is a force of attraction. So when you combine these two together, and do you mind just showing me on a single diagram how your diagram will look like? Or did you draw it on the dotted line already just now?
No, that one is different. I'll draw another diagram.
Right, it's fine.
A over R to the 12 should dominate. Because it's the square. So
which one is steeper? 1 over r to the 12 or 1 over r to the 6?
1 over R to the 12th power. Steeper.
And how would you be able to tell that?
Because of the square, R to the power 6 squared is R to the power 12. So it's 2 times, the degree is 2 times the R to the power 6 one.
What do you mean by degree?
The power that the R is raised to.
Okay, that's not called a degree because degree can have many meaning. Show me a diagram again, like to scale roughly how the R12 and R6 would look like. Just now the one you drew. Let me see if you got the scale and the gradient. The two you have drawn doesn't look so different. Can you make them more distinctive in like the feature in terms of the feature you mentioned just now?
Alright, yeah.
Like you said, the R to the 12 would be much steeper than the R to the 6, right?
Yep. Something like this.
Okay, cool. So both of them have asymptote at the x-axis and the y-axis. Your y-axis is potential, yeah, VR. V as a function of R. Okay, have you got the diagram where when you combine these two terms together, how they will look like?
Yeah. This one.
Wait, you got two dotted line there, so
It's to represent 1 over A over R12 and B over R squared, R6. So I just subtracted the dotted line.
okay. Let's think about this. All right. Let's consider this. When R is very small, when R is very small. Let's do when R is very big, because when R is very big, it's very easy. Okay. When
Yeah.
R is tends to infinity, do you think the sign of the potential will be positive or negative? Yes, it will tend to zero because they are almost the same value. One over like A over infinity tends to zero, B over infinity tends to zero.
Yeah.
But the difference between the term has a tendency. Does it tend towards zero in the positive potential direction, or will it tend towards zero from the negative potential direction? And suggest to me how. So we are talking about the shape of graph now. So before you even think about like all that thing in terms of like value of R or whatever, there are always three scenarios. Does it have an x-axis or y-axis? In this case, they don't because they are asymptote. Which if they don't, then you need to think of what happens when it's very large, when the variable is very large. In this case, when the x-axis tends to infinity, suggest to me or explain to me what do you think happens. Do you get the question?
Yeah.
Okay.
So A over R to the power 12, when R tends to infinity, then it's approaching 0 from the positive side, from the positive potential. And then for B over R to the power 6, when R tends to infinity, the potential of B over R6 tends towards 0 from the negative sign.
So how about their difference? Because the equation is an equation of the potential energy. So all I want to know is the potential energy going to be positive or negative when R to infinity?
A over R to the power 12 decreases faster. So that means it will be positive. Wait. B over. If B over R to the power 6 is smaller than A over R to the power 12, then large minus small, it'll be positive. So it's tending towards positive 0.
So are you saying that what you drew? So can you like sort of like have a y-axis, v against r, and then show me how it would look like when r tends to infinity. So just the tail end. I want to see the quadrant is in based on what you explained just now.
Okay.
So you got the tail end, yeah? Okay.
So large minus small.
Well, actually, I just want the tail end. So Most important thing in the graph is you forgot the y-axis and the x-axis, but you have drawn positive potential. Okay, let's go back to that. Okay, sorry, you can put the paper down. When you say large minus small will be positive. Okay, let me bring you back to this. Let's say R is 10. Let's say R is 10. Okay. No, let's make it 10 to the let's make it 10. It doesn't matter. 10, okay? A and B are just constant. When you have 10 to the power 12 and 10 to the power 6, they're going to be big, right?
Yeah.
So let's just say A and B are negligible. We're just playing with R equal to 10, but actually in reality, R tends to infinity. Okay, so 1 over 10 to the 12 versus 1 over 10 to the 6. Which one is bigger?
1 divided by 10 to the power 6.
Okay, so the left side is a smaller value than the right side because when R is positive and when R tends to infinity, 1 over something bigger will be smaller. So when R tends to infinity, what you have is a smaller minus a bigger value. Not the way you mentioned it just now, because this is reciprocal. Yeah, can you see that now? So therefore, when you have R tends to infinity, the R to the 12 will be a bigger term, and therefore the reciprocal will be a smaller term, and therefore what you have is you can come up with this. Inequality, sort of like 2 root minus. So can you see the inequality?
Yeah.
Can you see that?
Yep.
So therefore you get like a negative. It tends to negative. It's the other way around. So do you want to correct your diagram and sketch me the tail end? I just need the tail end. I don't need the rest because we are still figuring out how it looks like, you see. So let's just get that right first.
Oops.
Okay, so it will be, does it touch the 0? Does it touch the x-axis? It's an asymptote, yeah? It doesn't touch the x-axis, by the way, because it's a limit. It doesn't intersect with the x-axis. Because try to find the x-axis. Does it intersect the x-axis or not?
No.
How would you find the x-axis?
Substitute VR is equal to 0, and then.
So does it have an x-axis?
No.
Really? Can you try and do it? For that equation? For that A over R12 minus B over R6. So the x-axis is when you cut the x-axis, therefore that's when VR equal to 0, right? Yeah. So does it have an x-axis?
It does.
Oh, so just now you straight away say no, it doesn't have an x-axis. But now you say it does. So which one are you talking about?
If substitute 0 into the equation,
Okay.
then you're just solving A over R12 is equal to B over R to the power 6. So when they're equal, it cancels out. So you solve it, and then AR to the power 6 is equal to BR to the power of 12. And then R will be square root of A over B.
Square root?
Yeah.
Are you sure it's a square root? Can you check your maths?
Oh.
You cannot make a mistake like that. Huh? It's not 12 over 6. It's R to the 12 over R to the 6. And therefore, you should still get R to the 6 equal to A over B, right?
Yeah.
This is your classic form for normal maths, not even higher maths. The very basic of normal maths, the very, very basic of normal indices and stuff, okay? It's not 12 over 6, it's the power. It's different, okay? You can use logarithm and whatever, you can still come up with the same answer, but not 12 over 6, okay? Cool. So we know it has we know this graph has an x-intercept. But when R tends to infinity, it does not intersect because A and B are just constant. So there's just one x-intercept. There's no more than one intercept. Make sense?
Yeah, it does.
Okay. Can R be negative? Just another question. Because when you have R square equal to something, you can have plus minus. So technically, when you have R to the 6, you can have 6. Can R be negative in this context?
Negative distance. That means no.
Okay,
That's,
cool. Because this radius is not a displacement. Displacement can be like, if this is fixed, you are going that way, there's the R. That can be a distance, or it can be a displacement. They can have plus and minus. But this R is a scalar quantity, therefore it's just one dimensional. And therefore we don't consider a negative value at all. So it just cancels out, essentially, yeah. Okay, cool. So another thing you want to know in this graph is what happened when R tends to 0. So we know there's the x-intercept. We know R is like it approaching from negative potential towards 0, towards 0 on the potential from the negative sense. How about when R tends to 0? You should be explaining to me all these things, yeah, rather than me guiding you. But anyway.
If R tends to 0, the A over R to the power of 12 power decrease. The R to the power of 12 power decreases more. That means the reciprocal increases more than the reciprocal of R to the power 6. So the positive dominates because the reciprocal of R to the power of 12 is larger than R to the power 6.
Okay. So do you want to show me the other end of the graph and see how it's like?
Okay. Still.
Plot the tail end as well when R tends to infinity. And you forget the x-axis and the y-axis again. Those are very important feature of a graph. Yeah, when you sketch something, otherwise a graph has no meaning at all.
Yeah.
Okay. We also know it has an x-intercept. So it looks like the one where R tends to 0, it looks like it's coming down. Why would you say it's coming down and not increasing going up? What makes you say that?
Because the A over R to the power of 12 power is larger.
Again, what do you mean by larger? In what context is it larger?
The potential of 8 over 12, A over R to the power of 12. Oops.
You think it's larger? Okay. How about when R is, let's say, number 10, number 2, let's just say number 2. Okay. 1 over 2 to the power of 12 minus 1 over 2 to the power of 6. Let's just say A and B are 1. So is that positive or negative?
Negative. Because 1 over 2 to the power of 6 is larger than 1 over 2 to the power of 12.
How about when R is a half?
If it's a half, then 8 over R to the power of 12 is larger because if you divide by a fraction, then the whole thing increases.
Yep. So you understand the importance of number 1, right? Anything below 1, anything above 1, there's a difference, because anything below 1, when you square them, when you cube them, when you 12 them, they just get smaller because it's a power lesser than 1. If the value is bigger than 1, when you square, when you cube it, when whatever, the value increases. So it's the kind of graph that you should be aware of. Yeah. Okay, cool.
Yeah.
So it has an x-intercept. So do you want to show your graph so that it cut an x-intercept? Have you drawn it that it cut an x-intercept? Oh, you haven't drawn that it cuts an x-intercept yet. So maybe stretch it downward. So it cuts an x-intercept essentially.
Yeah.
because we figured those points out. So another thing is what happened between it coming down and it becoming a negative potential going to infinity. So what else feature of a graph would you be interested to find out? So look back at your individual graph of 1/R12 and 1/R6. How the graph would look like, or what would you do to figure out the other part of the graph?
Sorry, what was the question?
Do you think you can figure out how the other part of the graph will look like? And why? Or how you figure it out?
From if it's less than 1, that means the A over R12 dominates, but then if R is greater than 1, the B over R12 dominates.
Again, we are assuming that A and B are just one, but A and B can be any numbers, yeah. So I think we need to go into less generalization now. Anyway, the next part of a graph that's quite important for you to figure out that you should know from your normal maths is turning point. Does this graph have a turning point or not? It's a quite easy concept to find out, right? Like you got the features of a graph. It's very simple. When I ask you to draw a graph, very simple. But when I put two graphs together, what are you supposed to look for? Those are the key features, okay? So does this graph have a turning point?
Yeah.
Really? Does it?
Yeah.
How would you be able to tell? You don't just say something without having a reason.
Because A over R12 at one time it dominates, but then at another time B over R6 dominates. Eventually there should be a spot where there should be this decreasing.
You're cracking out actually, so I'm not sure it's my internet or your internet. Hello? Can you hear me? Hello? Hello? You are cracking out and you are lost. And hello? Are you coming back? Hello? Are you back?
Yeah.
Okay, your connection is really terrible. Yeah, okay. Do you want to say that again?
I
did not get that part. Yeah. Mm-hmm.
A over R to the power of 12, if it is as R increases, the 8 over R to the power of 12 will decrease. But then eventually B over R to the power of 6 will catch up and then it will increase more. Wait, it will increase from.
I think we need to talk more about physical meaning now. When you say increase and decrease is a mathematical value, yeah, okay? Let's talk about more positive potential or more negative potential. So more positive potential means it goes in the positive VR direction. More negative potential means it goes in the negative VR direction. It's better to talk in that sense because value does not have a meaning, but physical value have a meaning. In this case, potential energy. Okay, so you say there is a turning point. Then how can you prove there's a turning point? And if there's a turning point, can you find me the turning point?
Yeah.
Why is the connection really bad? Like you are really cracking up. Like yeah. Anyway, continue. Just continue. Did you get a question?
You can differentiate, and then yeah, how can you find the turning point? It should be where if you place the two charges, that means the turning point is at equilibrium.
Okay, can you find me the turning point? because in order to sketch the graph, you need a few key feature of a value, right? So such as the turning point, there's gonna be a value of the x-axis and the y-axis that you should be able to label on the diagram very easily.
Okay. To find the turning point, we need to differentiate. AR12 negative 12, VR negative 6. So, what do VR stuff. Differentiate doesn't give a nice value. That's so, 7. 15 minutes. 6. 2. 5. 6.
What have you got for me?
I got the position of the turning point is when r is equal to the 2 p. So it depends on the bed.
Do you want to your expression? Do you want to show me your expression for the equilibrium radius? Lift it up a little bit. Okay, it's focusing, but it's very blurry. Okay, is that 2a over b and then root power 6?
Yeah.
Okay. Okay, cool. So how about the y-axis value? What is the equilibrium potential?
Just substitute the. Okay. Substitute in r is equal to the 6th root of 2a over b. So the 6 roots can nicely cancel out. So it leaves me with a over 4a square over b square minus b over 2a over b. So I get b square over 4a minus b square over 2a. And then we can combine the fractions. B square minus this is 4. So this is
So you got minus b square over 4a?
Yeah.
Can you show that to me again? I just want to double check something. Okay, so you got a over 4a square over b square minus b over 2 over b. So that would be b square over 4a squared. There's a and a cancel. I'm trying to figure out where I have gone wrong. Where have I gone wrong? Okay, I figure out where I've gone wrong. Okay, you're correct. Yes. So you do get over 4 times 2. You get minus, you get a negative, minus b squared over 4a. Cool. All right. So that is the okay. I got something wrong. It's okay. Never mind. So you have equilibrium radius, but then you also have the intercept. The intercept when the potential is just zero, right? That's when the y-axis is zero. When the potential energy is zero. So which one is bigger than which? You think the radius, let's just call that R naught. So R naught is when the potential is zero. R equilibrium is when the, like you said, the potential energy it's at the minimum because the repulsive force balances the attractive force, right?
Yeah.
Okay. And then the R naught is when the potential is just zero. Okay, so which one is bigger? Do you think the based on the value we saw so far, like what you have done, the expression, do you think the R naught is to the left of the R equilibrium or to the right? So maybe you can sketch on your diagram now because you already know there's a turning point, and then you know the opening bit, and you know the ending bit, and you know the x-intercept, and you know the equilibrium radius and the equilibrium potential energy.
Yeah. So it intersects when R is equal to the 6th root of A over B. And then...
So I should say A and B are greater than zero, let's say. A and B are greater than zero.
And then the equilibrium position is when R is equal to the 6th root of 2A over B. So that means the equilibrium position is it's greater than the intersection on the R-axis.
Okay.
The turning point must be... So that means it starts from when R is equal to less than 6 over A over B. It starts from the positive quadrant, the first quadrant. And then it decreases and cuts the 6th root of A over B, and then turns at R naught. Nuts, please. Oops. But then it doesn't, it only intersects it once, so that means it just straight from the negative, from the 4th quadrant, it just it tends to 0. So something like this.
Yep, but you probably don't want to draw. Okay, again, do you see what's wrong with your graph?
The axis.
all you have got is just one value, and it means nothing at all. There's no x-axis, no y-axis, no level whatsoever. You got the shape correct. Yeah, it does look like that. Okay, good. Can I show you? It's actually a combination of both things. Yeah. So you see the top bit. There's actually the repulsive term that give you the positive potential, but then now it's the combination. Therefore, it gets there's a reduction effect from the negative potential, so it's slightly lower than that thing which curve really fast. It goes down and then it turns, and it also goes up as well. Happy?
Yeah.
Cool. It's supposed to look smoother than that. This is like up and down. It's like a well. Okay. Cool. Do you wanna talk me through what is happening on that graph? Like I mean to the right of the R equilibrium. So what's happening there, and what is happening to the left of the R equilibrium? So we already know at R equilibrium, the attractive force balances and repulsive force, like you said. That's why they come to a minimum, right?
Yeah.
And there's the equilibrium. It get balanced out nicely. So what happened to the right of the equilibrium radius, and what happened to the left of the equilibrium radius? So this is two atoms. One atom is assumed to be stationary, and the other atom is moving.
Yeah.
There's attractive and there's repulsive. That's the model. So come on.
To the
Floor
left
is
of
yours.
to the left of the equilibrium, the atom is going closer to the other one, so the potential increases because of the repulsion due to the electrons in the atoms with the electrons on the other atom. And then to the right of the equilibrium, when R is getting larger, the repulsion between electron is negligible compared to the attraction between the two atoms. That means they are oppositely charged, right? So that means at 6 root of 2a over b, that is the radius.
We just call it equilibrium radius is fine.
Okay, yeah, that's the equilibrium radius between the two atoms.
Yeah, so
that's the distance the bond length basically, right? If it was
we're not talking about a chemical bond yet. They haven't reacted yet. They are still just interacting with each other. So my question is, what happens to make it simple, right? You already got the gist of the concept correct already. Equilibrium is when the repulsive force balances out with the attractive force. So to the left and to the right, it's just a matter of which one dominates. So do you want to just simplify for me? To the left of the equilibrium distance, which forces will dominate?
The force of repulsion due to electrons.
Okay. Can you see in terms of physically what is happening? So the two atoms, they get closer and closer and closer. So the electrons will want to repel, right? Yeah. So this is just the nice distance. Because this is such a nice distance because there's that repulsive force as a result of that electron repelling each other. Hence, you have that other term rather than just attractive. What happens when gets so close together? You will need to put energy to make them come close together, right? Okay.
Yeah.
In fact, that's how chemical bonds actually form. They need to come so close together that they need to have activation energy, and then the electrons can get transferred and whatever. Then you get the bonding electrons that can form a chemical bond. Yeah.
Yeah.
How about at the other end?
The other end is the force of attraction between nucleus and electrons. Nucleus of one atom and the electron of the other, and vice versa.
Yeah, what are you talking about? You haven't explained anything. You said something about attractive force and something about vice versa. You mind clarifying yourself?
Force of attraction between nucleus and electrons. So it dominates the repulsion between the two electrons. So as R increases, the force of attraction dominates the force of repulsion, but then when R is greater than the equilibrium radius, then the nucleus gets too far from the electron, so the potential starts to decrease towards zero again.
Yeah, essentially, right? So, getting so far where there's no interaction between them anymore. No more potential because the distance gets so big, okay? The idea is that just now you were still talking about the left side of the equilibrium radius, which you should have finished talking about it when you talk about which forces dominate. So to the left side of the R equilibrium, there are two regions, right? When the potential is greater than zero, that's when the repulsive is still greater than the attractive, and it flips over to the negative potential as soon as the attractive dominates over the repulsive. And then obviously to the right of the equilibrium distance, that's when the attractive force is still anything which is negative potential, that's when the attractive force is still dominating over the repulsive force. But it's such at a point where greater than the equilibrium distance, the attractive force is still more dominant than the repulsive force. But again, it's getting weaker and weaker because it's getting so far apart until the potential eventually becomes zero and tends to zero. It doesn't become zero because of the asymptote. Tends to zero as R tends to infinity. Does that make sense?
Yeah, it does.
Okay, so that one is actually between atom and atom. So let's talk about Coulombic force. Okay, so imagine now you have a charged particle, not a proton and electron, because we already talked about that in the structure of atom. Let's talk about a cation and an anion. What kind of force do you think exists between them?
Force of attraction. Force of attraction means because the positive charge and the negative charge has their own electric fields.
Okay.
And the electric field of the positive one is going out, and the electric field of the negative one is going into the charged particle.
Okay.
And
So
the electric fields are in the same direction.
so
So that means
is there a, if you have a cation and an anion, let's just say Na plus and Cl minus, is there a force of attraction between them or not?
yeah, there is.
Is there a potential between them or not?
There is.
What's the relationship between force and potential energy?
Force and potential energy. Force is inversely proportional to the square separation, while potential energy, it's proportional to just the separation, just no square.
But why? Why?
But
How do you know that? Where does it come from?
force due to electric charges is the constant times Q1, Q2 over R square.
Do you want to write me the expression so that I can see where it is?
K is 1 over 4 pi E naught.
Oh, okay, cool. So those are just constant. We'll just leave it as constant. So what kind of force is that?
Electrostatic forces of attraction.
Okay, so we're talking about a cation and an anion, right? So there's definitely that kind of force because they're charged particle. Then that Q1 Q2 relationship. Each charge has a effect on the other one. So what effect do you think when you have a Mg2 plus versus a Na plus on the force of attraction?
Mg2 plus has a larger force of attraction because according to the equation, if you have 2 times the electronic charge 1.6 10 to the power negative 19, then the force would be larger than if it was just plus 1.
Oh, okay. You were multiplying by the single electronic charge, but then usually in terms of chemistry, usually like you see energy expressed in terms of like joule per mole, kilojoule per mole. So actually, we just multiply the whole thing by Avogadro constant to get it in terms of mole, so that it's easier. So instead of working with like plus 1 times E, we are just working with plus straight away because it's already multiplied by Avogadro constant. Yeah. So it's just the overall charge, and therefore your overall value will be in terms of per mole, rather than like times by E, because E is such a small number. Who wants to be working with 1.6 times 10 to the minus 90? It's easier to work with mole, right? Kilojoule per mole, joule per mole. Happy? Okay, cool. So how about barium 2 plus? So Na plus Mg2 plus, you say would be Mg2 plus would be stronger force of attraction, right? How about Ba2 plus? So we are talking about the same anion. I'm not going to tell what anion now. Let's say, let's just forget what the anion is, but it's the same anion. We're just changing the cation.
Okay. Ba2 plus is Ba2 plus is in a lower, it's much more further down the group than Mg2 plus. So that means
what group? What group are we talking about? Are they even the same group?
Yeah.
I don't know.
Group 2. Mg2 plus and Ba2 plus. So, and Na plus and Mg2 plus, they're in the same period. So that means Ba2 plus has a larger radius, ionic radii. So that means the charge density in Ba2 plus is
Less than what? Lesser than which one?
Mg2 plus. Yeah, Ba2 plus has
Okay. If I ask you to think about, okay, it's quite hard to. So Ba2 plus versus Mg2 plus, that's easy. A plus versus Mg2 plus is easy. Na plus versus Ba2 plus, there's no easy way to tell unless you know the actual value. Because one, they are from different groups, and two,
yeah.
they are of opposing charge. So it's a factor of which one actually wins. Is it the charge, the charge quantity, as in like +1 versus +2, or is it the ionic radius that wins? And you have used the right term, which is known as charge density. So charge density is charge over the volume size, which is the atomic radius, right? To the power of 3,
Yeah.
the volume of a sphere. So all this ionic model, they assume ions as spherical. The most important thing in ionic model is things are 100% ionic, just ions. They don't care about covalent character, they don't care about polarization, whatever. Things are perfectly spherical. Those are the two important assumptions. What's the volume of a sphere? If you know the radius, what's the volume of a sphere?
4 over 3 pi r cubed.
What's the surface area of a surface area? What's the surface area of a sphere? Can you have a surface area of a sphere? Yes, you can, right?
Yeah, 4
What's
pi
this?
r squared. 4 pi r squared.
What's the relationship between area and volume?
Area times a distance gives volume. So
what's the differential equation relationship, the mathematical relationship between area and volume? Do you know?
no. Oops.
Area is the differential of volume with respect to radius. Okay, so can you express volume in terms of area using the differential meaning, using all this calculus?
4 pi r squared d over dr 4 g pi r cubed.
No. I haven't really talked about it. I just want the general relationship between volume and area. So I just told you that volume is equal to dV over dr. Can you express V in terms of R? Not for sphere, just a general expression, just from that alone.
So wait, area is dV over dr.
Yeah.
We want to find V in terms of A.
So V in this case is
R.
volume. Yeah. V in this case is volume and not potential. What do you get? I just want the expression. I just want the general expression. Like, what's the idea from there? Can you get it?
Volume is equals to the integral of A with respect to dr.
Yeah. Can you try to prove it using the maybe if you have the volume of a sphere, which is 4/3 pi r cubed, right?
Yeah.
Can you get the area, surface area of a sphere from there? Did you get it?
Not sure. Oh.
Did you get 4 pi r squared?
Yeah.
Yeah? Okay. Now there's a relationship between force and potential energy. Okay? There's a relationship. So you know that potential energy is like the unit is in joule, right? So in a sense, it's a work done. Obviously, work done and potential energy are slightly different, but you can think of it in terms of energy. Energy is work done, is equal to force times distance. It's a derivative of force with respect to distance. So we're saying that energy is a derivative of force with respect to distance. So potential is equal to what was I gonna say? Force. So is that correct? Yeah. So potential energy is the integral of force with respect to distance.
Yeah. So that means.
Are you okay with that? So
Yep.
in terms of VR, V as a function of R is equal to integral of F with respect to dr. So now in terms of the Coulombic force of attraction between two ions of opposing charge, which you know the expression in terms of Q1 over Q2, Q1, Q2 over pi E not R square, which is just expressed as a constant anyway. Can you get me the expression for the potential energy between the cation and the anion? So what did we say the relationship between potential and force again? Can you say that to me again?
Potential is equal to df over dr.
Nope. That is wrong. That wasn't what I said. I said potential is the integral of force with respect to dr. Can you write down an expression for it to see that if you have gotten that right or not? For me, let me see. You forgot v as a function of r there. So on your left hand side, so your variable is dr, right? So your function can be of one variable, two variable, three variable. At A level, you just do one variable. So v bracket r means v as a function of r. That's potential energy with respect to distance. Sorry, potential energy as a function of distance is equal to the integral of force with respect to dr. That is totally opposite of what you said just now. Yeah. So this is the expression of what we said. Okay. So as distance changes, so we'll integrate over the distance which we apply the force in, and that will give us the energy. That's the expression. Okay. Do you know just now the expression for Coulombic force between the cation and anion? Can you obtain for me an expression for the potential energy?
Yeah. It's just negative k q1 q2 over r.
Okay. So what does this negative value tell you?
It's attractive force.
Okay. But what?
Wait. Force of it. If potential.
Sorry, I forgot something. Potential energy is equal to minus the integral of force dr. Sorry, I forgot about that. That's a minus.
Oh, yeah. Okay.
Then it makes sense, doesn't it? Okay. Does it make sense now?
Yeah,
I think it makes sense now. Okay. So tell me whether it makes sense or not.
Yeah.
How does it make sense?
Oh.
If Q1 and Q2 are oppositely charged, then the potential
Hi,
will be
Alex. Hello.
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 How are you doing? I'm sorry for
Okay.
disturbing. I didn't know.
Oh, it's okay. He's finishing soon. If we can finish this last problem.
Good luck. I'm gonna leave you now.
So if Q1 and Q2 are oppositely charged, then the potential would be negative because
Is that good?
yeah, because the question is the interaction between cation and anion.
Yep, and we just talked about potential energy between two atoms just now. Remember the negative potential? And that's good, right? The more negative it is, the more it's going down the well, and they will get attractive. Okay? Happy?
Yeah.
Okay.
Yeah.
Can R be zero?
Can R be zero?
In this context between the cation and the anion.
That means if R is zero, that means the two charges are.
They will attract, right? Cation attract anion, right?
If R is zero, the R can be zero. Yeah.
So you're saying that a cation can exist at the same place where an anion is. So you're saying that the nucleus of one atom can be where the nucleus of another atom is. You're saying that two things can be at the same place at the same time. Is that what you're saying?
If but then charge is just
That's a trick question, actually. So this is a model. The model is just assuming plus and minus. It's just assuming ions. It's just assuming charged particle. It's just assuming a
Yeah.
single plus and a single minus. It hasn't assumed, what it hasn't done is it hasn't complicated the model by saying that there's a nucleus and there are protons in there and there are things that cannot happen. And
Yeah.
when they get so close together, even though they are cation and anions, because there's the overall charge, because one has more proton than electrons, one has more electron than protons. But when they get close together, if they have outer shell electron and outer shell electrons, again, what will happen? Repulsion will happen. Yeah. Can you see that the graph will look there will be a repulsive force, and this model based on this equation is perfect only when there is perfect ions. But again, you need to put in another term, which is to account for the repulsive force as well. Repulsive
Yeah.
potential, sorry. Yeah. And then in a way, you will get like a similar kind of graph where it's going down and then going up again. Again, it's a equilibrium between the cation and anion. They are held quite nicely together in that fixed ionic lattice. They get so close together, they will repel. They get so far apart, that's when you break the ionic bond. Yeah?
Yeah.
But the expression is different because just now was the interaction between atoms, whereas this one is the interaction between the full cation and the full anion. But the idea is the same. Do you get the idea? Okay.
Yeah, I do.
Cool. So actually, so make sure you remember that, yeah, potential energy is equal to the negative integral of FdR. Okay, it's very important to have the sign correct because then you'll get the idea correct as well. Okay.
Okay.
And obviously, it works when the two things are oppositely charged. When the two things are of the same charge, then Q1 times Q2 will be positive, and you get a positive potential, which indicate a repulsive potential, right?
Yeah.
And that is bad on its own.
Mm.
Okay. So going back to that, potential energy is the negative integral of FdR. Going back to that original expression for potential energy between two atoms, can you get me the expression for the force the expression for the force with respect to R, force as a function of R, based on that potential energy equation? The very first one.
Force as a function of R.
Mm-hmm. Do you know the equation? A over R12 minus B over R6.
A over R negative into just equate it with the potential energy is equal to negative integral f dr with respect to R. So negative integral of f with respect to R is equal to A over R12 minus B over R12 So that means to get f is just to differentiate it. Differentiate with respect to R negative A over R12 plus B over R12 So negative times negative 12 is positive 12. And then 12, negative 12 minus 1 is negative 11.
Is that positive for the first expression or negative for the first expression?
Positive.
You've differentiated something incorrectly, man. It's R to the minus 12, right? So when you differentiate that, do you get r to the minus 13 or do you get r to the 11?
13.
Damn, man. And then the second mistake is the same thing. r to the 6 is r to the minus 6, so it's 1 over r to the 7. As a matter of fact, you already differentiated this expression once. Just now when you found the turning point, you already did it. So the fact that you could do it just now, you couldn't do it now, means something is very wrong. So what you should do is you should differentiate without the negative and then reverse the sign of the whole thing. You will get a positive 12a over r13 minus 6b over r7. I wouldn't go around and like change the sign each and everything. I will remember that there's a negative and then I just change the whole thing. That's the easiest way to go, rather than, I know in school they teach you like bracket this, bracket that. Yes, you can use a big bracket and then just remember to change that at the end. But you cannot make a mistake like that. R11 and R6. Yeah, that is a classic rookie mistake. And this is the kind of the two kind of physics question that usually come out. Attractive force, repulsive force. It's a balance between the two. Started out with sketching graph, a little bit of physics, a little bit of integration. Well, it's maths. It's maths, graph, physics. And in terms of the chemistry, it's just the concept of radius and the attractive force. Whether the attractive force or attraction is ionic bond, or is it just the effective nuclear charge, which is just between the nuclear. Sorry, not effective nuclear charge. Maybe something like metallic bond, because it's between. Oh no, not even metallic bond. I don't know, just some sort of interactions. They can give you a van der Waals equation. It's kind of similar as well. There's attractive force, there's repulsive force. Just always remember that, you know, like in school, you always learn electrostatic force attraction. There's something called repulsive force as well. Okay, that's the most important lesson of today. We'll let it be for today. But yeah, I hope you finish your application soon enough. Yeah. And any? Oh, have you decided on which college yet?
No, not yet. I haven't looked into it yet.
What have you been up to? There's a lot of things to be finished by then. Have you finished your first draft of personal statement yet?
Not yet.
How many drafts are you planning to do?
How many? I don't know. 2 or 3.
Typically, people go through 20 drafts for Oxbridge, yeah? 2-0. 2 and 3, who are you going to ask to read? Your brother? Your other brother? You know, you need to step up your effort, yeah? Okay, your personal statement is your first intention. Is your intention. Why am I doing this? Okay? It doesn't matter how smart you are, but you still need to make a statement about yourself. You still need to go through a few of those TSA, thinking skills, assessment paper. Those are multiple choice because you're just doing section 1. I won't be going through those with you because those you can do on your own. Should be all right. I mean, they're just mostly like thinking skills questions. Yeah? But yeah, any problem you have, just rest it out with other tutors. Okay, cool. Let it be for today. This video is recorded. I'll upload it later, and then you can just follow that if you need to. Otherwise, there's no need. Cool. All right. Any questions?
Actually, I read the book that you sent me, the one on chemical reactions.
Oh yeah, this was in there as well.
I was confused on the Born interpretation of wave functions.
Wave functions. Forget about that for the time being. We'll talk about it another time. But wave function is mostly onto the quantum chemistry already. So what about it that you wanted to know?
I know it's like wave function squares the probability density, and then what exactly is a wave function for the Born interpretation? For me, I'm confused.
When you say Born interpretation, is Haber-Born, right? Like Born, right?
Yeah, Born.
Okay. He's the guy who came up with the Born-Haber cycle as well. So he does a lot of things actually. Fantastic chemist. Actually, he won a Nobel Prize. You should read up on like some of the chemistry Nobel prizes. Yeah, like just in case they ask you like who inspired you in chemistry. You should probably know a couple of people, what they do, you know, like just to show that in fact, you should be interested in this general knowledge question. Speaking of which, I think Born-Haber was Danish. He was a goalkeeper for the Danish football team as well when he was very young. If you read out his Wikipedia. Wave function. First of all, you know probability is always positive between 0 and 1. That was the reason why they square it, because wave function can be positive or negative.
Okay.
So they square it to get a positive value, and then you can come positive and positive. Okay. Probability density is basically what orbital is. You know, like where an orbital, you always draw the electrons are fixed in one position, but in reality there is no such thing as a physical shell. So your electron is just circulating around anywhere around the sphere. It can go that way, but you always circulate around that fixed spherical region. And then the other electrons, let's say those are the inertial electrons, they will be on the outer shell circulating around their radius, their fixed radius around the nucleus as well. This is because they're in the other shells. Yeah. So their wave function will be different based as a function of r. That's why wave function is always as a function of r, radius from the nucleus. Okay. There is interaction between the electrons and the protons in the nucleus, and the wave function account for all that. Okay. And from there we can get the energy. And there's the basis of Schrodinger equation. Basically, he won a Nobel Prize in physics/chemistry. I think physics, quantum physics. That was how they solved to get the energy of a particle in a box. If you read up some stuff on Schrodinger cat problem, there will be an idea on like wave function, energy of a particle. In 3 dimensions, there's x, y, and z. X, y, and z are the simplest thing. You have those things called quantum mechanics, quantum chemistry, quantum physics. It's essentially just quantum physics. But there's also classical physics, which I'm sure you learned in your physics. There's something called Equipartition Principle. Have you heard of Equipartition Principle?
No.
Have you heard of the root mean velocity?
Yeah, root mean square.
Yeah. Have you heard of 3/2 kT, Boltzmann constant time temperature?
Yeah.
And you can convert that into, so Boltzmann is for one single atom, one single particle, and you can convert it into mole by multiplying by Avogadro constant, and you get 3/2 RT, right?
Yep.
Yeah. Okay. Where about in physics do you learn this?
Ideal gas under.
Where does the 3/2 come from?
3/2.
Why do you get 3/2? Where does that number come from?
The 3 comes from the fact that there's 3 sides of a cube. And
where does the half come from? What does the half mean?
what does the half mean?
Do you guys learn this as well, or do you guys just learn the formula?
No, we learned this, I don't know, trying to remember.
Oh, well, these are basic assumptions that you need to remember for chemistry as well, okay? The equipartition principle says that for every translational axis, this is just talking about translational, so x, y, and z, there is a half kT contribution to energy. So if you can vibrate, so solid can vibrate, vibrate again. One is translate, one is rotate, and I forgot what's the other one already. Vibrate is the highest one. Translate, rotate, vibrate. So translate first. So translation, you can have x, y, and z. If you have a particle, in each direction, they will have a half kT contribution towards energy. Okay. In 3 dimensions, where the gas particle can go x, y, or z, then you will sum them up. Half kT plus half kT plus half kT. For each particle, there is 3/2 kT. And for 1 mole of gas, you get 3/2 RT. There's the equipartition principle, actually, the half kT contribution for each degree of freedom. Where does the word degree of freedom comes to mind in chemistry?
Degree. Degree of, that's double bonds, isn't it?
Really? Degree of freedom?
Freedom.
Entropy rings a bell. Yeah, do you do degree of freedom and entropy?
No, I never heard it.
Oh, what's the definition of entropy?
A measure of disorder.
Oh, okay. So if you have more freedom to move, do you have more disorder or less disorder?
Yeah, more disorder.
There you go. That's the degree of freedom. So okay, you learn it in terms of disorder. But something which is disorder means it's free to move. And when you are more free to move, you have more entropy. And that's where you link entropy with enthalpy, with Gibbs, and also with the half kT, because there is a thermodynamic phenomenon. And these are classical thermodynamics. Whereas all that wave function and things, they can link very well. They can explain the classical phenomenon by explaining it in terms of quantum chemistry.
Yeah.
Okay. So going back to half kT, let's go back to half kT first. So when things can rotate, so what kind of thing can rotate? When you have one single things like neon, argon, single atom, right? They just have the half kT, half kT, half kT, 3/2 kT contribution. When you have things like HCl molecule, what they can do is they can rotate. Rotation means rotate that way, and rotate that way. So things like HCl doesn't make too much of a difference, because HCl, even though there are 3 degrees of freedom, but one way or the other is the same. So you actually only have half kT plus half kT. It doesn't have 3/2 kT.
Oh yeah.
Can you see that? Because one of it is essentially the same. These are talking about statistics now. Okay. Are you following? Are you sure you are following? Okay. Whereas things like, let's talk about CO2. CO2 is a linear compound, so it's very interesting. How many degrees of freedom does CO2 have in terms of rotation?
CO2, it's symmetrical.
Yeah. So you can think about it rotating in 3 dimensions, right? So each degree of rotation, meaning each degree of freedom, will contribute half kT. So we know it can translate. We know the CO2 can go X, Y, and Z. So that is 3/2 kT. But how about the rotation? So it can rotate as well. So I just want to know what's the contribution to the rotation. Is it 3/2 kT, or how many degrees of freedom are there?
Only one, because they're all the same.
1, 2, 1, 2, 3. Can you rotate? Can you rotate?
Okay.
And what have I done? I've done that way. I have done this way. And you're right. CO2 is symmetrical. There's only one. How about C double bond O and then S on the other side?
C double bond O what?
S. So replace one of the oxygen with S.
S.
Sulfur.
Sulfur. One, 2.
That one is different. That one is different. That one is the same. Yeah, yeah. Can you see why one of it is the same? Because it's still going back to the same position when you rotate about the axis. Yeah, when you do that, it's still exactly the same. So it's the same degree of freedom. It doesn't contribute at all. So here is where this is actually, they probably wouldn't ask this in interview, but I've heard some of my friends, they got asked about ideas of degree of freedom, which is essentially just statistics. So they throw molecules at you and think about the rotational movement and trick questions like this. Are they going back to the same position, or are they different? Okay. Yeah. But wave function, I've forgotten most of my quantum already, to be honest. But wave function is basically a function, a mathematical expression, and it's a model, by the way. A model can only be so, and you have to add further things to the model to account for certain things. Okay, and to solve this kind of mathematical expression, they can use supercomputer, because unless you really want to spend all day working through the maths, it's quite complicated maths. Yeah, for 1 dimension, okay. 2 dimension, getting more complicated. 3 dimension is complicated. 3 dimension for 1 atom is okay. 3 dimension for 2 atom is complicated. And then think about the extra dimension, time again. So we are assuming that they are fixed. But what do we know about them? they are moving. When you
Yeah.
introduce time, no way you can do by hand, man. No way. Actually, they did. They spent many years doing by hand. That's how they won the Nobel Prize.
Oh,
But then obviously now we have supercomputer to do it already. So no one does it
Yeah.
anymore. It's a model. It's a mathematical model. And because it's a wave function with respect to R, you can integrate it and then you can solve it. And then with an expression, you can draw a graph and then it will have a meaning. Okay?
Yeah.
Fair enough? Any other question?
Not yet.
Okay. Don't spend too much on the wave function. Maybe you should move on to the bonding and then the organic bit is quite. But yeah, I mean, just continue reading and then you can always come back to it or ask me the next time. Cool.
Okay. Yep.
All right. Have fun. Okay.
Right.
Bye.
Thank you, sir.
All right. I'll stop the recording. Where's the? It's alright. You can hang up. I'll find the stop recording button.
Okay.
Fine.